Good morning, everyone. So this talk is about a novel SARP system capable of flash irradiation, and I'm Mohammad Rezaid at the Department of Radiation Oncology and Molecular Radiation Sciences at Johns Hopkins University, and this work is funded by NCI AIP grant, and this presentation is unrestricted. So here is the acknowledgement for the people that are involved in this project at the Johns Hopkins University, University of Pennsylvania, and also the XRR company. So at present, most irradiators used for flash radiation are complex machines. As explained, as shown in this slide, for example, the cyclotron, synchrotron are producing proton beam at ultra-high dose rate. Also, the electron linacs producing electron beams at flash dose rates. But most of these radiators are not readily accessible for preclinical laboratory research, and a limited center may have access to this irradiator. In addition, electron beams has a dosimetric characteristic, that is the lateral dose spread in the median as shown in this slide. In the simulated dose distribution of 6 MeV electron. In contrast, the KV X-ray beam is a sharp beam with a minimum length for the penumbra, but KV X-ray beam has high depth dose gradient. So it would be ideal if we extend the capability of current cabinet X-ray irradiator that currently is available in the biological labs to support flash radiation. So we start to think about to use that type of irradiator about 2 years ago. So we work on the SARPs, and we try to see the feasibility of this system to provide the flash irradiation. So we assume a 2 cm thick water phantom attached to the tube at the closest distance to this focal spot to get the highest dose rate. And then we simulate the result using the Monte Carlo GN4 platform. At the surface of the phantom, the dose rate reaches up to 45 gray, but it drops to less than 20 gray just in a few millimeters as expected due to the inverse square effect. Then the KVP X-ray beam from a single X-ray tube have high dose rate gradient. Then we look at to the different machine, the 60, which is available in our lab, and this machine use a parallel opposed X-ray tube, 2 X-ray tube in the parallel opposed geometry. So uniform depth dose rate is achievable by parallel opposed X-ray sources. And then we simulate again, attaching both tubes to the 2 cm thick water phantom, and then calculate the dose rate in the phantom, and we observe that the parallel opposed X-ray sources with minimal filtration provide lower end dose rate, which is about 40 gray per second of intended flash irradiation. So it's not really a good system for flash irradiation if we are going to extend the current available cabinet system. So then we think about a new system. So this new system, which we call it SARP flash cabinet system, utilizes high capacity rotating anode X-ray tube at the power of about 100 kilowatt and at the maximum energy of 150 kVp in a parallel opposed geometry. So the diagram in the middle of this slide shows one of the setup for the simulation is the water phantom with a thickness of 2 cm, which is located at 9 millimeter distance from the exit window of each X-ray tubes. And on the right side, we will see the dose rate curve as a function of depth inside the water phantom. So using the parallel opposed geometry at the very close distances, we are able to get flash dose rate above 100 gray per second in the center of the water phantom. And also we can see, due to the parallel opposed geometry, we can have a uniform depth dose with a plus minus 5% deviation within 10 millimeter at the central region of 20 millimeter thick water phantom. So in addition, a maximum delivered dose with this system can be up to about 50 gray at 1 cm depth in that phantom. So in addition to the flash radiation, this system also is capable of providing the conventional dose rate irradiation by increasing the separation distance between the X-ray tubes and also reducing the tube current. So as shown in this diagram, when the tube separation distance reaches to the 40 cm and the beam current reduces to 5 milliamp, the dose rate in the center of that phantom is less than 0.1 gray per second. One of the concern that we may have in this design of X-ray tubes, usually when we have the parallel oppose geometry, the entrance dose and the exit dose will be high, as shown in the blue curve in the right side of these slides, compared to the center of the phantom. So this system is able to angle the beam to avoid the overlap of the beams from two X-ray sources. Then it reduces the surface dose in the phantom, as we see on the red curve, is significantly reduced compared to the phantom center. So some of the properties of this SARRP flash cabinet system is that this system does not need any mechanical shutter because the X-ray beam can be turned on and off within the 5 milliseconds, which is very important for the flash experiment. Flash beam can be delivered in a single pulse or multiple pulses, which is also very good feature if you are going to study the mechanistic studies of flash effects in both biology or even the chemistry. A wide range of dose rates, about 0.05 to 200 gray per second, can be selected with high resolution and controlled with very low uncertainty, usually less than 5%. And the collimation can be achieved with 1 or 2 millimeter thick tungsten because the energy of this system is 150 kVp. So the collimation and even shielding is much lighter compared to 220 kVp X-ray beam. And image guidance can also be implemented. So we installed a single flash X-ray tube in our labs and started to do some dosimetric measurements. So first, we used the field measurement in water phantom to measure the output, PDD, profiles, and output linearity with exposure time and current using a 3D printed film holder with a 1 millimeter resolution. So this curve shows the PDD curves at 5.5 cm from the focal spot using the copper filter. And we will see that the depth dose does not drop very fast because we have the filtration and we remove all low energy component of the beam. So at 5 millimeters, still we have about 90% of the dose and the dose rate. And at the exit window, we can get a dose rate about 120 gray per second. So these two curves also shows the linear relationship between dose and exposure time and current, which is a very good linear relationship, and it shows that we have a very good control on adjusting the dose rate of this system. In terms of the profiles, we can, because this is a single X-ray tube, we can see the Hill effects in that curve. And but we are using, the field size is 2 by 2 cm, and we are using the 1 cm field size and the opposite direction of field effect as shown in the dash rectangle area in the curve. That is the irradiation field that we use for our animal experiment. And in that field, the dose rate is about 81.1 plus minus 5 gray per second. So we are also starting a simple in vivo model study, so investigation of flash effects on mouse skin induced by KV X-ray flash beam. So we actually use the skin murine model irradiation with various dose levels from 30 to 45 gray under flash, which is the 90 gray per second dose rate, and conventional dose rate, which is about 0.1 gray. And we will continue these studies for other marine models like I and GI with the flash and conventional dose rate. And in summary, so this feasibility study shows that the SARRP flash cabinet system can provide KV X-ray beams at both flash, which is up to 200 gray per second dose rate, and conventional, which is less than 0.1 gray per second. And this system can be utilized in the research labs and engage larger groups of scientists for mechanistic and translational study of flash irradiation and its biological effects. Thank you very much for your attention, and I'm happy to answer if there is any question.
Can you hear me, Mohammed?
Yes, I can.
I just want to question your standard parallel pulse system using the conventional dose rate of 40 kilowatt. That's not using the standard power of 4.5 kilowatt, right?
Right. Yeah, usually the current system in the lab uses the stationary anode X-ray tube that the maximum power, I think is a 6 kilowatt, but usually they use at the 4.5 kilowatt in the lab.
But your results show a hypothetical 9 kilowatt.
Right. Even if we go, so my result is we assume that if we have to the very high end, it's a hypothetical 9 kilowatt X-ray tubes, then still we are in the lower end of the dose rate we need for flash studies. Right, but this is based on using the minimal filtration that actually remove all the electrons and low energy photons in the beam.
Dr. Rezai, there was a question that came in through the chat from one of the attendees that says, do you plan to increase the dose rate further?
So the increase of dose rate is really dependent on the technology. We need more powerful and even at the higher energy. So if that technology is available, yes, we can use that. And also it depends on the request of the user, then it may entice the industry to work on that technology also. But this system can provide up to 200 gray per second. Even it can be higher if we are irradiating the superficial lesion like a skin. If we have a parallel oppose and really bring very close to the sample, we can get up to 250 gray per second.
Okay, thank you. And one more, have there been any in vivo studies on this system?
Any what study?
In vivo.
In vivo study, not yet with that system, and we are starting to do that. So we already irradiated, as I mentioned in one of my slides, we already irradiated the mouse skin with that system, and we are waiting for the results.
Thank you.
I think there is only one published paper for X-ray irradiation. And again, that X-ray is from a synchrotron X-ray, which is about, the average energy is about 100 keV, if I'm right. And they observed the flash effect at a dose rate of 37 gray per second. But our system is different because it uses a single pulse in our study.
Okay, thank you. Well, I think we will likely conclude But thank you, Dr. Rezai, for this interesting and informative presentation.
You're welcome.